Welcome to part 3 of my series of videos where I'm using artificial intelligence to identify birds on my bird feeder. At the end of the second part, we got to the point where I could take static images from my bird feeder, run those through a customized data model and identify the birds that were on it. Now this time, what I want to do is be able to take a video stream from my bird feeder, dynamically run that through a data model in real time and identify the birds on the feeder. Let's go and take a look how. Hello once again, Pi geeks and techno nerds all around the world. My name's Jeff and I'm an IT professional who's been in the industry for over 30 years. I've been using Raspberry Pi since they first came out, and I wanted to share with you some of the projects that I've done over the years. If you like what you see on this channel, hit that thumbs up button, subscribe to see more, and also hit that notification bell so you can be told when I put a new video out. Also, let me know in the comments how you get on with this project, and if you've got any ideas for projects for me to do in the future, let me know in there as well. Now, when I first started thinking about how to capture a video stream from my bird feeder and then use artificial intelligence to identify it, the first thing I thought of was some software called Frigate. Now, Frigate is a completely open source software that behaves kind of like Ring cameras available from Amazon. You give it details of an IP web camera and an artificial intelligence data model, and it will then identify objects that pop up in your camera's view. So I went ahead and I set up my camera in Frigate to see what would happen. And on the whole, it kind of worked okay, but it was very limited. Here on the events page, you can see that it has picked up an awful lot of detections of birds on my bird feeder. However, it's labelled them all as a person. And what's really strange with Frigate is even though it does allow you to use your own custom data model, it has a kind of predefined set of labels that it applies to it. You can override that in theory, but I was never able to get it to work. And as a result, any bird that landed on my bird feeder was just classified as a person. Frigate is very much geared towards identifying people and cars and various other things that you would typically see going past a house. It's really not suited for this particular case. The other thing is that if I open one of these detections, it will play the video that was recorded at that particular time, and that's really nice. But you can see there's no annotations on the video at all to show what bird was detected. If I go to snapshot, it will identify where the bird is, but again, it's labelled as a person, and the thing is, it won't show you that actually on the video. And that's what I want to do. I want to dynamically view a video feed from my bird feeder and have that annotated in real time showing where the birds are. So rather than using Frigate, I've developed my own software to do it. Now all of this is running on a regular Raspberry Pi 5. There's no extra hardware involved at all aside from the IP camera itself that's looking at my bird feeder. Now, as always, I've got a GitHub repo and I've got the software available for you to pull. All you have to do is drop down the code button, take a copy of the link, then on your computer type in git clone, paste in the link to the repository and hit enter. And there you see it's pulled all of the code down. If you move into the UK Bird Classifier Part 3 directory, you'll see all the files there. Now let's go and take a look at these files in a bit more detail. Here you can see the first piece of code that I wrote. It's called webcam.py. And this is a class that defines all of the functionality to interact with my IP webcam. Now here, I'm using a great third-party library called OpenCV. This is a wonderful way to be able to capture frames from an IP webcam and then process them. Here in the constructor, I accept as parameters the URI of the webcam, and by that I mean the HTTP URL to access the video camera's stream. Now if you're unsure how to get the stream for your particular camera, take a look at my video here on the subject. I go through that process in depth, making use of a website called iSpy. This is a wonderful resource for figuring out how to get hold of the streams on your particular web camera. I also allow the width and the height of the image that comes in from the web camera to be provided as parameters as well. I then set up a local property called frame that is initially undefined. In this next section, I open up the stream from the web camera and I set the properties about it within OpenCV. I then provide a method that can be used to see if the feed from the webcam is active. I then have a method to read a frame from the webcam, so this will just read in literally one frame from the video camera, and it will return that to whoever wants it. Now, as you'll see a little bit later, the AI software needs the color space for the video to be specifically in red, green, blue format. Now, by default for my camera, it's coming in as blue, green, red, so I have to do this conversion. The other important bits here are a way that I can signal OpenCV to stop capturing, and then have a way to terminate the processing of the video stream. Now, my main software doesn't actually call this last method at all, because I'm actually outputting another stream of video. However, if you want to show a frame of video that you've captured within a separate window, you can use this particular IMShow method within OpenCV to do that. So I just expose that as another method within my class. This next class handles the opposite side of the processing. Here, I'm using an application called ffmpeg to open up a video stream that I'm then outputting frames into. Now, as you can see, the options for this are really complex, but I'll give you a quick summary. The -f raw video is saying that when I'm sending images to ffmpeg, they're going to be absolutely uncompressed raw video images. They're effectively kind of similar to JPEGs, but just not compressed at all. I'm then saying that these are going to be converted back to blue, green, red, that every image I send it is going to be 640 by 360 pixels. The frame rate is going to be 8 frames per second. Now that doesn't sound very high, and I'll explain why a little bit later. The -i hyphen means that ffmpeg will read from its standard input. And what's great is that within Python, I can get hold of ffmpeg's standard input pipe, and I can then just send data straight into it. And so this line here is just telling ffmpeg just to read from that pipe. I then tell it to use the libx264 codec to encode the video. I have to provide what's called a pixel format for the video. I won't go into terrible detail about that here. It's really a very complex video thing. Needless to say, if you're doing this yourself, just copy that value. I then have a few options that define what's called the GOP structure for the video, and again, don't worry about that right now. In a nutshell, it's kind of defining some rules around how the video is compressed. But again, it's a very complex topic in itself. The next option is to tell ffmpeg to focus on speed as opposed to quality when it comes to the encoding process, so encode as fast as it possibly can. The -f FLV is telling ffmpeg to encase the video content within a Flash video container. Now, Flash video hasn't really been a thing in the industry for several years now, but for the specific protocol I'm using, it still uses that format. I then provide the URI of where I want to send my video stream to. Now here, I'm giving it what's called an RTMP endpoint. RTMP is a streaming protocol, and whilst it's not too popular now, it's still great for sending video around as long as you're on a pretty reliable network. Now, in order to provide an RTMP endpoint, I'm using some software that I actually set up in a prior video regarding capturing video streams from your own IP webcams and then exposing those in your own websites with your own security applied. You can see all of the details on how to set all of that up in this video here. But in a nutshell, it's using NGINX as a web server and a plugin for NGINX known as the NGINX RTMP plugin in order to set up the RTMP endpoint. Now, in my other video, I went through in some detail how to set all of this up, but the important thing in this case is this section of the NGINX RTMP plugins configuration file. Here, I'm creating an endpoint that I'm calling birdcam_live. I'm saying that the live stream is enabled, and I'm also providing configuration to also have the NGINX RTMP plugin convert that to another streaming protocol called HLS, which is really good for using on web pages. So just as a reminder, if you're accessing the video stream on your own local network at home, then using RTMP to access it will work just fine. But if you're trying to access it from anywhere else in the world, RTMP isn't going to work very well. HLS as a protocol is specifically designed to allow video streams to be viewed on regular web pages. So that's why I'm making the stream available in both of these different formats. Jumping back to my code for handling ffmpeg, as well as the method for getting hold of the pipe for standard input, I also provide a method that can be used to stop ffmpeg from running. And then I expose a method for actually writing a frame of content to ffmpeg. So this just takes a frame as a parameter and it just writes it to that standard input pipe. This next class is where things get a little bit more interesting. This is a class for actually doing the AI analysis. So the first thing I do here is to allow 3 parameters to be passed into the object. The first being a reference to the data model. That's exactly the same file as we created in part 2 of this series. I then allow a threshold to be provided. And this is the minimum confidence score that the AI model will have in order to have a detection show up. There's then a maximum number of results or detections that I want to have per frame, just to keep things moving reasonably quickly. I then set up some placeholders for our detection data. I say that our target is to hit 8 frames per second for the output. I also have a placeholder for just keeping tabs on what the current frames per second is. Now I'm using a library called MediaPipe to do all the artificial intelligence here. It's really just an extension of TensorFlow. So here I'm just initializing the options for that by giving it the reference to the data model. I then provide a whole bunch of other options for the processing, and then I start up the data model. Now for everything that the data model does detect, I then have this method here for saving those results. So this gets called every time an individual detection is made. I then have a method here to enable a frame that's been captured from the webcam to be added into the analyzer to see if it finds any birds within it. This method here then actually runs the AI model against the captured frame. Once all of the detections have been found, I can then call this method here to update the frame with all of the detection points. So it will do things like draw little boxes around everything it's found. And just like for the web camera and for ffmpeg, I provide a method to shut everything down again. The next class here is what I call my visualizer. This is the code that will actually annotate the frame, showing you what the current frames per second is, and also actually labeling where the birds are. Now I show the frames per second figure in a box in the top left of the frame. So all I have to do is draw some text in that top left-hand corner, specifying white as a background so that the text appears on effectively a white box. The draw text method is what actually does that. So here it will draw a rectangle that's filled with the background color that you specify. And then on top of that, it will write some text in the color that you want. This method is used to actually mark up where the birds are that have been detected within the frame. The main part of it is the for loop. For every detection that's been found in the image, it will draw a box around the area where that particular bird has been found. I then draw a rectangle just on top of this that I can then use to overlay the text saying what type of bird it is. And then here I actually draw that text. And you'll see what this looks like in a demo later. Now, if things go wrong, I wanted to create myself some customized exceptions that I can use within my error handling so that I get all of these special exceptions rather than anything generic. So I know exactly what's going wrong. The main application code pulls all of this together. Here I've got a class to represent the main application. It's constructed by passing in all kinds of data here. So you've got the URI for the camera, a reference to the data model, the threshold defining how confident you want the model to be when it comes to detecting birds, the width and height of the image, the URI of the output stream, and the maximum number of results to show. I then construct a webcam object, and if that doesn't work, I capture one of my customized exceptions. I then create one of these ffmpeg objects to create my RTMP output, and I create the AI analyzer object to actually do the analysis. And finally, I create the visualizer object to visualize the results. The main bulk of the code is here in the run method. For all the time the webcam is open, I record the time when I actually start this iteration. I read a frame and I keep a copy of that for use later. I convert that to RGB, add that to the AI analyzer, and then I detect any birds that are in it. I then use the visualizer to update that copy of the original frame that I took earlier with the frames per second information. I then call into the AI analyzer to render all the results, giving it the visualizer as a parameter, along with that output frame. Once the image has been marked up, I then write that to my ffmpeg output. And again, if anything goes wrong, I make use of my custom exceptions here. I then have this code to say, if I hit the escape key, then the application will exit. I then record when this particular iteration ended, and from that I work out how long it took to do the detection. Now I've found for a Raspberry Pi 5 that 8 frames a second is just about enough time for all of the AI to work and the video encoding for the output stream. If I try to go above that, then I find the Pi gets a little bit overloaded. So in order to cap this at 8 frames a second, I just subtract however long all of this took from 0.125 seconds, and then I just sleep for whatever the difference is. That way I can guarantee that I'll never output more than a frame every 0.125 seconds or 8 frames per second. And once the webcam's been closed, I close everything else. Now when I actually run this file, I grab all of the information I need from environment variables. And the reason I do this is because it makes my life a whole lot easier for running this as a Docker container. And you'll see more of this in a minute. I then create my application object from all of that data that's been captured from those variables, and I run it. Now, I ultimately want to run this application as another container within Open Media Vault that I have running on the Raspberry Pi 5 that I have as a NAS. This Dockerfile sets up the Docker container. So I use the ARM version of Ubuntu 22.04 as a base. I bring all of that up to date with the latest packages. I then go through installing all of the packages that I need in order for all of this software to run. And one thing that's very important at the end of that list you can see there is ffmpeg. I then create a directory where I want to put all of my software, and I want to run this using a specific version of Python. Now in my last video, you will have seen me using software called pyenv in order to install a very specific version of Python so I could build my custom data model. I'm going to use exactly the same software here within my Docker container so I can be really prescriptive of the version of Python that I use in there. Following on from installing pyenv, I then install all of the environment information that I need. And just to make all of that persistent, I update the .bashrc file within the container. I then install and make global version 3.12.4 of Python. Now the reason I do this is because I can't guarantee that my software here will carry on running with all future versions of Python. They'll probably enhance the programming language, and at some point it's not going to be compatible anymore. So this way, I know that my software will run because I know it can work against this specific version. Just to really lock that in, I then create a virtual environment for my Python code. I then install all of the Python modules that I need after upgrading the pip tool. I then add in all of my Python code along with a shell script that's used to start up the application. I then specify that I'm going to have a directory here that's going to be mapped from my host box, and that will provide the location of my bird model. So that way, as I keep on enhancing my bird model over time, training it with more and more data of more and more varied birds, I don't have to keep on rebuilding the container every time. I can just use volume mounting to change the model that's used. I then set some default values for those environment variables that I was mentioning earlier. And I specify the entry point for the container as being that docker-entrypoint.sh shell script. Now if we take a look at this docker-entrypoint shell script, it's really not very complex at all. All I do here is take the parameters that were passed to the shell script, which is the value of all of those environment variables, and I re-export them again within this shell script. This is going to be running within its own instance of bash, and I want to make sure that all of those variables are available. It is actually quite easy for these things to get lost. I then just run the application. And you'll notice here that I actually used the Python executable that's within my virtual environment to run the application. And this is what absolutely guarantees that I'll use that 3.12.4 version of Python. Now I've jumped over to the Raspberry Pi 5 that I'm going to run this code on. I've already pulled all of my code from GitHub onto here. And now all I need to do is build the Docker container. And you can do that with this command here. Docker build -t birdcam_AI:001, although that's just the tag that I used. You can call this whatever you like. -f, and the name of the file that contains all the instructions to build the container, in this case Dockerfile. And then after a space, I have a dot there showing that all the resources it needs to build the container are here in the current directory. Now that's all built. Now I like to run this using Docker Compose. I like to use Docker Compose because otherwise you have to put all of the parameters there on the Docker run command line, and it can get really complex and unreadable. Whereas if you make use of a Docker Compose file, everything is laid out really nicely. So here I'm saying I'm going to run up a container that I'm going to call birdcam AI. I'm going to set its external name as birdcam AI. So if I run other things like docker exec or docker logs, that's the name that I'll use. I want Docker Compose to always automatically restart this application unless I've shut it down cleanly myself. I then specify the ID of the Docker image I just built, so that tag birdcam_AI:0.0.1. And here is where I pass in my TensorFlow Lite model that I built in the last video. If you haven't built your data model yet, just take a look at my last video right here, and it will show you how to do that. It's a fairly long process because you've got to go through providing all of the different training data, but it's not actually that difficult. And once you've done it, you just end up with this single file that you can then make use of here. And apologies for the trickery where I've just had two variables appear here. I didn't realize I'd missed them out of this file. But here I just provide those environment variables. The first one is how to access the video stream on my camera. The second is where my RTMP stream is going to be. The third is the threshold for detections. And the last is where the container can find my data model. Now I could have hard-coded this within the container since I am using volume mounting to put it in a very specific place. But I just thought for flexibility, why not? Now I've covered this many times, but if you don't have Docker already installed on your Raspberry Pi, you can just run sudo apt install docker docker.io docker compose, and that'll install everything. On my system, everything's already there, so it's just flashing up there's some conflicts. You won't see that if you're installing this for the first time. Running the application as a Docker container using Docker Compose is now really straightforward. You just have to do Docker Compose -f and the name of the Docker Compose YAML file, in my case birdcam.ai.yaml, up -d. And there you can see the container's been started. If I run docker ps-a, you can see all of the containers that are running on my system. There's quite a few of them, but you can see the birdcam container is one of them. There's also my NGINX container that I covered in an earlier video that's running the NGINX web server, and then there's the container that I'm using to run the NGINX RTMP plugin. So all of these will work together in order to allow me to capture from my web camera and publish to that RTMP stream, and also view everything as an HLS web page. Now, stopping the container from the command line is just as easy. You just have to execute this command here, docker compose -f birdcam-ai.yaml down. And that will stop the container and clean everything up. Now, a few videos ago, I set up Open Media Vault running on my Pi 5 acting as a NAS. And one thing I was able to set up on here is the Docker Compose environment. And so you can set up all of your Docker Compose applications right here within Open Media Vault and manage them through that UI. So here I've set up the container for my Bird cam, and if I hit edit on that, you can see that it's just got the same data. I've got the specifics here for my particular webcam and my RTMP endpoint, but all the rest is exactly the same as we saw earlier. And then on this interface, if I just select BirdCam AI and I hit the up icon, that will start up the container exactly the same way as we did from the command line just now. And now that's running, and I could access the video in exactly the same way. So how do you actually view the stream? Well, the first way you can do this is within the VLC application. If you open that up, then click on Media and open Network Stream, then you'll be shown the box that you can see here. Now, the IP address I've got highlighted there is the IP of my Pi 5, where I'm running not only my container for processing my BirdCam video feed, but I also have the NGINX RTMP module running on there. So I can therefore access the RTMP stream that my AI code is generating. And then if I just click the play button, it will connect and show me the stream. And as you can see, it's identifying birds in real time. Now, another way that you can view the stream from the camera is by using this web page I've provided within the GitHub repo. This is quite a simple web page that just contains a div element that in turn contains a video element that can be used to play the video. Within this JavaScript here, I load our stream into the video element and then the script goes on to play it. And so I've updated the configuration for my NGINX container that's also running the NGINX RTMP plugin. So now the web page and the stream are on the same box, and that's really important in order to avoid cause errors. And if I now navigate to the URL of that web page, I can see that the stream is displayed within my browser, and it's updating just fine, and you can see the birds that are identified. So as you can see, this has achieved everything that I wanted to with this project. I've got my live view from my webcam with it being updated in real time, showing what birds are on it. So as you can see, the container is running really nicely, and I'm able to view the video from my webcam with it all being marked up where the birds are. But where do I go from here? Well, my first thought is here. I've got a point where I'm picking up the birds have been found in my video. So one thing I could do here is add some code in here to do something like send myself a WhatsApp message or an SMS notification. So something would ping on my phone to let me know that there is a bird at the bird feeder. Another thing I could do here would be to trigger a second ffmpeg process that would record the frames that I'm sending to my output RTMP module as a small file. For all the times that there are detections being picked up within the individual frames that I'm capturing, I could keep that recording going and then just stop when the AI model doesn't find anything anymore. That way, I could replicate the functionality within Frigate that's allowing those little video clips to be saved out and reviewed later. Now, all of that is beyond the scope of this video, so I'm not going to go into any of that here. It's just some thoughts for what I could do in the future with this, or what you could try out yourself. Now, the one other thing I do want to do, again, not in this video, but in the next part, is make all of the AI detection go faster. There's custom hardware that you can get for a Raspberry Pi 5, and it attaches to the PCI Express port, and you can leverage this to make all of the AI detection go much faster. Now, I'm quite excited to try this out, and so I've ordered one of these kits. However, I'm not quite sure when it's going to arrive. So make sure you subscribe and hit that notification bell so you know when my video on that comes out. It may not necessarily be the very next video that I do. But that's all for this video. Once again, if you like what you see here, please hit that thumbs up button, subscribe to see more, including that part where I accelerate the AI, and hit that notification bell so you know when it comes out. Let me know in the comments how you get on with this or any other AI project that you try. And once again, if you do have any ideas for projects that you want to see me do in the future, put those in the comments as well. Thanks so much for watching till the end, and until next time, bye for now.